In this video tutorial, we will introduce the concept of equilibrium with a focus on Le Chatelier's principle. So back in grade 11, you probably would have learned that once your limiting reagent had been converted into products, the reaction is over. But that's not entirely true. In reality, most chemical reactions do not proceed to completion as they are reversible, and that's why we use this arrow over here, the equilibrium arrow, to show that both the forward reaction and the reverse reaction are possible. In grade 11, you were limited to just the forward reaction. We only focused on reactants being converted to products, but in actuality, products do have a chance to recombine back into their original reactants. Now, before we move any further, let's do a quick little detour and talk about collision theory. This theory is used to explain factors that affect rates of reactions, so how quickly reactants are being converted into products. You see, when atoms collide, there is a small chance that a chemical bond will form between the two. This is known as an effective or successful collision. In general, there are two requirements for a collision to be successful. The first is for the reactants to have the correct collision geometry, meaning that the reactants must collide with the right angle in order to form the correct chemical bonds. Let's watch this quick little video clip to better understand this concept.
Consider the reaction of two AB molecules to give products A2 and B2. The reaction takes place only when the molecules are oriented in such a way that atom A is able to react with atom A and atom B with atom B. When A meets B and B meets A, the reaction yields unchanged reactants and no net reaction takes place. Any other orientation will result in the molecules ineffectively bouncing off one another. The collision is effective only when the mutual orientation of the molecule allows the reaction to occur. Note that you can find only one correct effective orientation and thousands of others which are ineffective. This means that the probability of the correct orientation occurring is quite low. For this reason, most collisions are ineffective. That explains why many reactions are so slow. Still, it is amazing that some reactions are so fast.
Now, the second requirement of a successful collision is that it must occur with sufficient energy. We call this activation energy, in order to overcome the repulsive forces between electron clouds. Let's watch another video clip to help you visualize this.
Consider a very simple reaction of A and B to give the product AB. The molecules of A and B must collide for the reaction to take place. The collision of two molecules is different from the collision of two billiard balls. Molecules are not hard, elastic objects with definite, sharp outer boundaries. Instead, the electron cloud of a molecule is rather soft and fuzzy. When two molecules approach each other, their electron clouds come into contact and mutually repel one another because of their negative charge. The closer they come to each other, the stronger the repulsion. When the electron clouds of molecules penetrate each other to such an extent that a reshuffling of electrons becomes possible, the reaction occurs and a new bond forms. Slow-moving molecules possess insufficient kinetic energy to overcome the repulsion between electron clouds. The collisions of such molecules are ineffective. Only when the combined kinetic energy of colliding molecules overcomes the intermolecular repulsion can the collision be effective and chemical reaction take place. This minimum energy required for the reaction to occur is called the activation energy.
So to recap, in general, there are two requirements for a successful collision to occur. The first is that the reactants must collide with one another in the correct manner, meaning the atoms must be in the right area so that they can form new chemical bonds. If the atoms are in the wrong location, then a new bond won't form, or the incorrect bond would form. Once the correct atoms are side by side, they must collide with enough energy so that their electron clouds can overlap with one another. This allows the nucleus of this atom to latch onto the electron cloud of this one, and the nucleus of this atom to latch onto the electron cloud of this one. In so doing, they may share electrons, thereby forming a new chemical bond. Now, trying to get these two things to occur at the exact same time is very, very difficult. Thus, the probability of each individual collision being successful is extremely small. However, with quadrillions of collisions occurring each second, enough will collide successfully to allow the reaction to move forward. Keeping this in mind, there are 4 factors in general that affect the rate of successful collisions. The first variable or factor is concentration. By changing the amount of reactants or changing the pressure or volume of the container that they are in, we can change how crowded or how concentrated the reactants are. Now, this doesn't mean that we're making each collision luckier or more likely to succeed. Instead, what we're doing is we're increasing or decreasing the number of collisions per second. So for example, if I increase the pressure on a container, I will decrease its volume. In so doing, I've changed the concentration. I've placed all of these molecules in a much smaller area and made it more crowded, thereby increasing the concentration. In so doing, I've made it more likely for these molecules to collide with one another, so there are more collisions per second. Now, let's say 1% of all collisions are successful. That's being very generous. Less than 1% are usually successful. But let's pretend 1% of collisions are going to be successful. Well then, in this case over here, where the molecules are very spread out, there's fewer collisions. Let's say 100 collisions each second. Well, 1% of 100 means that only 1 successful collision occurs per second in this scenario. But by squeezing them into a smaller area, they're more likely to collide with one another. So now I have increased the number of collisions. Now, even though the success rate is still 1%, but 1% of 1,000 means that there are 10 successful collisions per second in this scenario. So remember, I haven't made each collision luckier. The chances of success are still 1%. But by increasing the number of collisions, I've changed the rate of success per second from 1 to 10. It's like buying more lotto tickets. If I buy more lotto tickets, my chances of success have increased. But the likelihood of each ticket being successful remains the same. The ticket doesn't become luckier just because I buy more of them, but I do increase my overall chance of successfully winning the lottery if I buy more tickets. Now, if we increase the temperature of the system, we also increase the average kinetic energy of the particles inside of it. So kinetic energy is the energy of motion, and by increasing the temperature, we increase the energy, we increase the speed at which these particles are moving. When these particles move faster, they collide with one another more often. So again, we have essentially increased the number of collisions per second, not by making them more crowded, but by making them move faster and hit each other more often. So once again, we have another scenario where we've increased the number of successful collisions per second. Now, another thing to also consider is that increasing the temperature also increases the number of molecules that have the minimum activation energy to start a successful collision. Imagine, if you will, a energy versus number of collisions graph. All right, so most of our particles will have a certain amount of energy. Some will be higher energy, some will be lower energy. And this is the activation energy. So this is the amount of energy required to have a successful collision. By increasing the temperature, not only do you increase the number of collisions, but you also shift the entire graph to the right. Now more of these particles are moving faster and are able to slam into each other with enough energy, so activation energy, to increase the number of successful collisions per second. So once again, increasing the temperature will increase the number of collisions. This in turn gives you more successful collisions per second. But increasing the temperature is a double whammy. Not only do you have more collisions, you're giving these particles an energy boost. So more of them are able to slam into each other with enough force to overlap their electron clouds. This energy boost will shift the graph over to the right, resulting in more successful collisions per second. Now the next factor that can affect the rate of a successful collision is surface area. By increasing surface area, we increase the number of collisions. We know that powdered sugar dissolves a lot faster than a single solid cube of sugar. So in this image over here, the red particles can only collide with the blue particles on the outside. The blue particles that are stuck on the inside cannot be collided with. The red ones can't reach them. But by breaking up the blue particles into smaller pieces, we have now increased the surface area. So not only can we have the red particles collide with the ones on the outside, the red particles are also able to collide with the blue particles that were on the inside as well. This in turn increases the number of collisions per second, thereby increasing the number of successful collisions per second. Our final variable is that of a catalyst. Let's watch this quick little video clip to understand how they work.
Consider the potential energy diagram for the exothermic reaction. Reactants give products. If the reaction is to occur, the reactants need to possess a joint energy exceeding the activation energy. As we can see from the Maxwell-Boltzmann distribution curve, only a few reactant molecules have sufficient energy. The reaction will be very slow. What happens when the reaction is carried out in the presence of a catalyst? Catalysts lower the activation energy for the reaction. Now many more molecules have an energy level exceeding the new, lower value of the activation energy. The number of effective collisions increases, and the reaction rate rises. Catalysts reduce the activation energy by providing an alternative route for the reaction. In other words, an alternative reaction mechanism. For example, the hydrolysis of esters like methyl ethanoate is relatively slow when the ester reacts with water. The reaction requires the lone pair of the oxygen atom in the water molecule to approach the carbonyl carbon atom. There is only a weak partial positive electrical charge on this carbon atom. Therefore, the attraction of the water molecule to the reaction site is not very strong, and so the reaction has a high activation energy. Ester hydrolysis can be catalyzed by acids, though. A positively charged hydrogen ion bonds to the oxygen carbonyl atom. A carbocation is formed, with one positive electrical charge situated on the carbonyl carbon atom. A water molecule is attracted to this reaction site much more strongly. The reaction has a lower activation energy and can proceed much more quickly. Addition of acid alters the reaction mechanism. The single-step reaction with a high activation energy is replaced by a two-step reaction with a much lower activation energy. Notice that the hydrogen ion is recovered at the end of the reaction. As the catalyst, it is not chemically changed in the course of the reaction.
So, as we saw in that video clip, a catalyst typically works by lowering the activation energy for the chemical reaction. It does this by providing an alternate reaction pathway, so a different way to react, one that requires less energy than the original reaction. In the example that was given, with the original reaction, the oxygen atom of the water molecule had to collide with the carbon atom of the ester. But because there's only a slightly negative charge and a slightly positive charge, there's a very, very weak attraction between these two sites. As such, a high amount of energy is required for these two to be pushed together to collide. We can lower this high activation energy requirement by adding in a catalyst. In this case, it's going to be the hydrogen ion that is released by an acid. That is then attached to the oxygen atom, resulting in the formation of a carbocation. Now in this course, you don't really need to know what a carbocation is, but essentially the carbo part stands for carbon, and cation because it is positively charged. So this is just a temporary situation. Once that hydrogen atom latched onto the oxygen, it resulted in a positive charge around the carbon atom. So instead of a weak partial positive charge to attract the oxygen atom to collide with it, that requires a lot of energy, this very positive carbocation makes it a lot easier to attract the oxygen atom towards it, thereby requiring less energy for the oxygen atom to successfully collide with the carbon atom with the correct collision geometry. So, as you can see, the addition of a catalyst has provided an alternate reaction pathway, so a different way to react, one that requires less energy than the original reaction. And at the very end of it, the H+ ion is released back into solution, so it was not actually consumed or used up during this chemical reaction. As such, it is not considered to be a reactant, nor is it considered to be a product. As it doesn't participate in the overall net reaction, we prefer to write the catalyst over top the arrow to show that it helps to speed up the reaction. It helps to allow the reaction to proceed faster. Alright, so before we move on to the next section, let's go over some key terms. In this course, we'll be looking at three types of systems: open systems, closed systems, and isolated systems. In an open system, both matter and energy are allowed to move freely between the system and its surroundings. So example of this would be a hot cup of coffee. I can add coffee in, I can take coffee out, I can add energy in to heat it up, and I can take energy out to cool it down. So both matter and energy are free to move in and out of my system. In a closed system, only energy can move freely in and out of the system, not matter. So long as this can of Coke remains sealed, I can't take Coke out, I can't put things into the can, but I can heat it up and I can cool it down, so I can allow energy to move in and out of this system. Finally, with an isolated system, neither matter nor energy can move freely between the system and its surroundings. And an example of this would be the perfect thermos. Now, even though the perfect thermos does not exist, as long as it is of high enough quality, and as long as our experiment is short enough, the amount of energy that leaks out of it during our experiment should be negligible. And if it is negligible, very, very little actually leaks out, we can assume that it is a perfect thermos, or at least it behaves like a perfect thermos. So in this course, equilibrium can only be reached in an isolated or closed system. Equilibrium cannot be reached in an open system. So if the variables like matter and energy are constantly moving in and out of your system, how can you ever reach a steady state if everything's always in a constant state of change? That being said, when the rate of the forward reaction is equal to the rate of the reverse reaction, the system is then said to be in a state of dynamic equilibrium. So let's take a look at this reaction to see how a dynamic equilibrium can be established. Here we have N2O4 decomposing into two separate molecules of NO2, one over here and one over there. At the very start of this reaction, so at time index 0, only the forward reaction can proceed. The reverse reaction is not possible because there's 0 NO2s at the beginning. So at the start of the reaction, there's no NO2s. Without any NO2s, how can they recombine to produce N2O4? As such, only the forward reaction is possible, where the N2O4 will decompose to break up into these two NO2 molecules. So once again, at the beginning of this experiment, only the forward reaction is possible, the reverse is not. But what happens at this point, 1 second later? Well, the N2O4 concentration has decreased. It had a high concentration, now the concentration is lower. This lowered concentration decreases the rate of the forward reaction because now that there's less N2O4, well then there's less N2O4s breaking up each second. So that has decreased the rate of the forward reaction. So I'm going to show that the arrow has shrunken in the forward direction. On the other hand, the concentration of NO2 has increased. Now that there are NO2 molecules available to combine together to make N2O4, the reverse reaction is now possible, so I'm going to draw a reverse reaction arrow. Now what has happened at the 2 second mark? Again, we see the concentration of N2O4 has decreased over time, meaning there's less N2O4 breaking up each second, thus the forward reaction becomes smaller and smaller and smaller. So that's why you see a progression of the arrow going in the forward direction, shrinking over time. Meanwhile, the concentration of NO2 is increasing over time. Because they're more concentrated, they're more likely to collide and combine with each other, thereby making the reverse reaction more likely to occur. And so, as you can see, with an increasing concentration of NO2, I'm increasing the rate of my reverse reaction. And so my arrows are getting bigger and bigger and bigger over time. Now, eventually you will get to a point where the forward reaction rate and the reverse reaction rate have become identical. So for every one N2O4 molecule that breaks up, one N2O4 molecule will reform. Going back in the reverse direction, they'll recombine and create another one to replace the one that broke up. It is here that we have established a dynamic equilibrium, where the rate of the reverse reaction and the forward reaction are identical. Now remember, in an equilibrium, the final concentrations don't have to be equal. So let's pretend the final ratio is 5:3. I'm just making this up. So these values don't have to be equal. Instead, it is the rate at which they're being converted in the forward reaction and the reverse reaction that makes them equal. Now, an interesting thing about equilibrium is that provided that the system conditions and total mass remain constant, the same dynamic equilibrium will always be reached whether we start from pure N2O4, pure NO2, or a mixture of the two gases. So in this example, we started out with N2O4, but no NO2s. But so long as the system conditions and total mass remain constant, so long as they don't change, we will always reach this ratio of 5:3, even if I start out with the exact opposite. So I start with NO2 and no N2O4s. The same result of 5:3 will still be reached once it's allowed to reach equilibrium again. Of course, the starting points don't have to be all or nothing. It can be a little bit of each. just so long as the system conditions and total mass remain constant, the same dynamic equilibrium, the same ratios will be achieved in the end. It just might take a little longer or a little shorter time to reach that equilibrium, that's all. Alright, so before we move ahead, let's introduce a few new terms. The first is homogeneous equilibrium, and the second is heterogeneous equilibrium. In a homogeneous equilibrium, the states of matter are all identical, they're all the same. While in a heterogeneous equilibrium, the states of matter are going to be different. So pay attention to these key terms. Quite often I'll see students get tunnel vision and they'll focus too much on the numbers in a question and not enough on the key terms in the question itself. And then you end up missing out on key information that may help you to solve the problem. Our next topic is on Le Chatelier's principle. It states that if a system at equilibrium experiences an external stress, so a change in concentration, volume, temperature, or partial pressure, the equilibrium will shift in the direction to counteract this change, and in the process a new equilibrium is established. Now I like to summarize all this in 2 words: damage control. So it's not damage reversal, so you're not going to completely reverse the change and bring it back to its original equilibrium state. Instead, it's damage control, where you're just minimizing the change in the system itself, so it's not going to be as bad as it could have been. Now, be aware, we're not trying to personify the reaction. Right? It's not like the equilibrium system knows which direction to shift in order to minimize the change. All of this can be explained using collision theory. All right? So Le Chatelier's principle is almost like a cheat sheet to tell you what to expect to see. But in the end, we explain what happens using collision theory. So let's watch this next video clip to better understand this concept.
Molecules of gas collide continually with the walls of the container, exerting pressure on them. The more molecules bounce against the walls, the higher the pressure. In other words, the pressure of the gas depends on the number of molecules per unit volume. Let's try to predict how changing the pressure will affect the equilibrium existing between chlorine, Cl2, phosphorus 3 chloride, PCl3, and phosphorus 5 chloride, PCl5, in the gas phase. When the pressure increases, the molecules are forced closer together. Now there are more molecules per unit volume. According to Le Chatelier's rule, the system will try to minimize the imposed change. The pressure can be reduced by decreasing the number of molecules. This is achieved by shifting the equilibrium to the right. Chlorine starts to combine with PCl3 to give PCl5 product. After some time, a new equilibrium is reached. What happens if now the pressure is relaxed? This time, the system tries to compensate for the pressure decrease by increasing the number of molecules. PCl5 molecules dissociate into PCl3 and Cl2, and the reaction proceeds in the opposite direction.
So, as we just saw, the gas particles are constantly moving, and as they move, they collide with the walls of the container. The more they collide with the walls of the container, the higher the pressure exerted on the container walls. In the first scenario, we had 7 molecules of gas colliding with the walls of the container. By increasing the pressure on the container and decreasing its volume, we have forced these molecules into a much smaller volume. This makes things more crowded and increases their concentration. In so doing, we have given the forward reaction the advantage, because now the Cl2 and the PCl3, because they're more crowded, are more likely to find each other, are more likely to collide with one another, making the forward reaction more likely to occur. PCl5, on the other hand, does not experience the same advantage. It doesn't need to collide with another molecule to go in the reverse direction. So forcing it into a smaller area doesn't really help it to decompose any faster or any better. So going in the reverse direction is not really affected, advantaged or disadvantaged by increasing the pressure and decreasing the volume. Unlike the Cl2 and the PCl3, where forcing them into a smaller area does help them to find each other, does help them to collide with one another, and thus improves the forward reaction rate. So originally we were at equilibrium, but then the pressure was increased, forcing the molecules into a smaller region so that they are more crowded together. This in turn made the PCl3 and Cl2 more likely to find each other, thereby increasing the rate of the forward reaction, while leaving the rate of the reverse reaction relatively unchanged. This allows the PCl3 and Cl2 to combine together into PCl5, increasing its concentration while decreasing the concentration of the PCl3 and the Cl2. So looking back here, we originally had 7 molecules inside the container colliding with the walls, exerting a certain amount of pressure, but because we're moving over to the right, we're shifting forward, and 2 molecules become 1. And thus we now have only 5 molecules in total exerting pressure on the container walls. With fewer molecules colliding with the container walls, the pressure inside has decreased. So, by increasing the pressure of the system, it forced the equilibrium to shift to the right, which resulted in a decrease of the pressure, because there are now fewer molecules in the container. And that's Le Chatelier's principle. We increased the pressure of the system, and it shifted its equilibrium to decrease that pressure change. But again, it's all about damage control, not damage reversal. We're never going to bring it back to its original pressure state. All we can do is reduce the damage so it's not as bad as it could have been. All right, so decrease the pressure back to a more lower state, but it won't decrease the pressure back to its original state. And so Le Chatelier's principle helps us to predict what's likely to occur, but in the end you must use collision theory to explain how it happened. In the opposite scenario, where we've decreased the pressure, in so doing we've changed the volume, and that of course has made things less crowded, less concentrated. Since they are now less crowded, these two are unlikely to find each other. It's more difficult for them to collide with one another. So in this scenario, rather than think of it in terms of an advantage, it's easier to think of it as a disadvantage. Since going in the forward direction is less likely to occur, I'm going to shrink the forward direction arrow, leaving the reverse direction arrow unchanged, and as you can see, the reverse direction now has the advantage because of the disadvantage of the forward direction. And so the PCl5 concentration will decrease, while the Cl2 and PCl3 concentrations will increase. So starting off with 5 molecules in total slamming against the walls, there's very little pressure exerted on the walls. But since we're moving to the left, we're shifting to the left and creating more molecules, we now have 7 molecules altogether in the end, and because there's more molecules colliding with the walls, the pressure has once again increased. So again, here's the scenario where we've decreased the pressure. It shifts the equilibrium to the left, making more molecules, separating 1 and turning it into 2. This in turn increases the pressure, so just as Le Chatelier predicted, by decreasing the pressure, equilibrium shifts to increase the pressure back up. Now, once again, you can't just blindly believe in Le Chatelier's principle. There are some situations where you can put a stress on the system without affecting the equilibrium. One such scenario is by adding an inert gas. So an inert gas is one that does not participate in the reaction. Typically we use noble gases as examples because noble gases tend to be very stable, they're unlikely to react, they're very unreactive. But be aware that the word inert just means it does not react. So any gas that does not react with our specific reaction is considered to be inert. It doesn't have to be a noble gas necessarily. In any case, because the gas is inert, it does not react or participate in the reaction itself, it doesn't provide a benefit to either side. So if neon does not react with either of these chemical compounds, then adding neon into my system won't help the SO3 to go forward and won't help the SO2 and the O2 to recombine, so it doesn't provide a benefit to either side. So when we add the neon gas, it makes the container more crowded. This in turn increases the pressure inside the container. Now, according to Le Chatelier's principle, if you increase the pressure, equilibrium should shift in order to decrease that pressure. But that's not going to happen here. Let's pretend this is a 1 liter container, and there are 16 of these red molecules, so 16 moles per liter, and there are about 24 of these gray molecules, so 24 moles in 1 liter. By adding in these neon gas molecules, did it change the concentration of these molecules over here, red and gray? The answer is no. They still remain 16 moles per liter and 24 moles per liter. So the addition of neon gas has not affected the chances of these molecules colliding with one another to go forward or reverse. There was no advantage or disadvantage to either side, to either direction. Now I know that some students may say, sir, adding in neon gas, doesn't that make things more crowded? Doesn't that interfere and prevent some of these particles from colliding with one another? Doesn't that cause a disadvantage? Unfortunately, this image is misleading. It looks like it's crowded here, but in reality, gases are mostly empty space. All right? The likelihood of a gas particle colliding with another gas particle, very, 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 very low in the first place. So although this diagram may look like the neon interferes, in reality, the interference is negligible. Collisions between particles is a lot rarer than this diagram would lead you to believe. But the key point to take home is that the neon gas does not interfere with the concentration of these reactants and products, nor does it interfere with the reaction itself because it does not participate. It is inert. Since neither the forward direction nor the reverse direction is advantaged or disadvantaged, the increase of pressure in this case does not lead to a decrease in pressure because it does not shift equilibrium. So be careful, don't just blindly follow Le Chatelier's principle and just do the exact opposite of what was done. In the end, you must use collision theory to verify which direction, forward or reverse, gets the advantage or disadvantage, and if it does not affect the reverse or forward directions, then it has no effect on equilibrium. Alright, now if you recall, the addition of a catalyst lowers the activation energy, so it provides an alternate reaction pathway, one that doesn't require as much energy to make it to the other side. As such, this increases the rate of reaction in both directions. So it's easier to make it to the other side going the forward direction, as well as making it to the other side going the reverse direction, as compared to the uncatalyzed reaction pathway. As this cancels out, catalysts do not shift the equilibrium, so the forward direction nor the reverse direction, neither side gets an advantage over the other. Both of them get the advantage. As such, this allows the system to reach equilibrium faster, so we're allowed to make it to the other side faster, but it does not actually shift the equilibrium, does not give preference to one side versus the other. Alright, now let's take a look and see what happens if you change the temperature. How will that affect the equilibrium? Well, first we need to identify if the reaction is endothermic overall or exothermic overall. So, as a review, in an exothermic reaction, energy is released from the system to its surroundings. So in this chemical reaction, the reaction itself would release energy to its surroundings. So if you touched the reaction itself, it would feel hot because energy is moving from the system into your finger. So you're heating up your finger, it will feel hot. Conversely, in an endothermic reaction, energy is moving from the surroundings into the system itself. So it's being absorbed by the chemical reaction. So if I tried to touch the system, it would feel cold because energy is being removed from my finger to go into the reaction itself. I'm losing energy from my finger, so it's going to feel cold. Now in this course, we can represent this energy change in the chemical equation in two different ways. In the first method, we write out the chemical equation, so reactants being converted to products, and off to the side, in brackets, we write down delta HR. So delta means change, H stands for the heat, and R stands for the reaction. So the change in the heat of the reaction, or if you will, the change in the energy of the reaction. And in this case, we have a negative energy value, so negative 80 kilojoules. The symbol here, negative, represents that the energy is being lost by the system. So we always have to view it from the viewpoint of the system. Don't think of it from your viewpoint, right? You are irrelevant. We need to think about it from the viewpoint of the reaction itself. And since this reaction is releasing energy, it's losing energy, it's giving energy up into the system, it is a negative value from its viewpoint. With endothermic reactions, it's the exact opposite. Because energy is being absorbed, I have to add energy into the reaction. Because I'm adding energy into the reaction, from its viewpoint, it's gaining energy. That's why it's a positive symbol, positive 80 kilojoules for the heat of the reaction, or the change in energy for this reaction. So once again, this positive and negative value is not from your perspective, it is from the perspective of the reaction itself. Is it losing the energy, the reaction, or is it gaining energy, the reaction? With the second method, we are going to, again, write out the chemical equation, reactants being converted products, but instead of having it in a bracket off to the side, we write the energy directly in the equation itself. Because the energy is being released by the reaction, it's being produced by the reaction, we consider it to be a product. So we're going to write the energy directly in the product side. Versus in an endothermic reaction, energy is written on the reactant side. It is a requirement for the reaction to move forward. So I need to give it energy in order for the reaction to move forward, so I must write the energy on the reactant side of the equation. Please note that it is plus 80 kilojoules, not minus 80 kilojoules. This minus and plus sign is just there to tell you, is it being lost or is it being gained? That's it. But because we're writing energy directly in the equation itself, you must place it on the product side and say it is an addition to the products. You are also creating energy. So it would be incorrect to write it as minus 80 kilojoules because that wouldn't make any sense. That would be like saying your reactants turning into products and your reactants are turning into minus energy, how can you create negative energy? That doesn't make any sense. So what's really happening is your reactants are being converted to products, and not only are you making products, but you're also creating energy. So adding energy. So in addition to the products that are being created, you're also creating energy or releasing energy from the system into its surroundings. Similarly, in an endothermic reaction, we have energy as a reactant. It is a requirement. In order for the reactants to turn into products, I have to add energy into the system. So because I'm adding energy into the system, 80 kilojoules must be a reactant, or written on the reactant side, it is a requirement in order for the reactants to turn into products. Now, keep in mind that in the forward direction, this is an exothermic reaction. Energy is being produced. It's on the product side. But if I talk about it in the reverse direction, so the reverse reaction, it now becomes endothermic, because now 80 kilojoules is required to go in the reverse direction. It's a requirement. I need to have it to turn the products back into reactants. And vice versa. If in this direction, forward, it's endothermic, in the reverse direction, it is exothermic. So switching the direction changes the energy sign, and of course, changes the energy requirements. Either it's being produced or it's being required to move in that direction. So in this reaction, going forward, we see that energy is a requirement. I need energy to break the N2O4 into NO2. As such, the reaction is endothermic. But if I were to write it in the other method, instead of writing the energy on the reactant side, I would just off to the side in brackets write delta HR equals positive 58 kilojoules per mole, because I must add energy into the system itself. Anyway, what happens if I increase the temperature of the system? How will that affect equilibrium? Well, by increasing the temperature, I've given the forward direction a boost, an advantage over the reverse direction. That's because moving forward requires additional energy, while moving in reverse, you'll notice that there's no energy written on this side, so going in reverse, additional energy is not a requirement. Room temperature provides more than enough energy for you to move backwards, so the addition of more energy is just wasted on this side over here. This side does require that energy. So providing this reaction with more energy gives the forward direction a boost, resulting in a decrease of N2O4 because we're using it up now. Since we're going forward, it's getting used up. And energy is also getting used up. And in return, we're producing NO2 because we're moving forward. We're making more NO2s. Now take a look at this. We gave it energy, so we increased the temperature. But by moving forward, we absorbed that energy and converted it from thermal energy into chemical potential energy. So the energy went from thermal energy to energy stored within the chemical bond, so potential energy. So just keep in mind, you can't create energy, you can't destroy energy. It can only be converted from one form into another. And in this case, we're converting it from thermal energy into chemical potential energy stored in the new chemical bonds that we have formed. Now, if you recall, according to Le Chatelier's principle, whatever you do to the system, it'll try to minimize that change. It'll try to reverse the damage, right? So in this case over here, by moving forward, I increase the temperature, it moves forward, and it consumed some of that energy, the additional energy that you provided, right? Because you're converting it from thermal energy to chemical potential energy. So now you see that the actual energy change is not as bad as it could have been. I raised the temperature by this much, but it got consumed and converted to a different form of energy. So in reality, I didn't raise my temperature by this much. I only raised it by a little bit. So it wasn't as bad as it could have been. So there you have it, Le Chatelier's principle, damage control. All right? It could have been a lot worse, but because the equilibrium shifted and tried to minimize that change, it's not as bad as it could have been. In the next example, we have increased the concentration of O2. So if you recall, when we put square brackets around a compound, we are typically referring to its molar concentration, measured in moles per liter. So in this case, we have boosted the concentration of oxygen. In so doing, according to the collision theory, we've made it more likely for the oxygen and the SO2s to collide with one another. Because they're more likely to collide with one another, the reverse direction gets an advantage. In so doing, we decrease the amount of O2 because we're using it up to go reverse. We decrease the amount of SO2 because we're using it up to go reverse. And we're increasing the amount of SO3 because we're producing now as we go in reverse. And once again, according to Le Chatelier's principle, we have minimized the amount of change, right? So initially we increase the concentration of O2, it shifts the equilibrium to the left, and in return, we consume some of the O2. So it's not as bad as it could have been. I increased the oxygen by a lot, but it consumed it back down, so it minimized the damage. It wasn't as bad as it could have been. So, a common question you will encounter in this unit is to either interpret a concentration time graph or sketch a concentration time graph. Let's take a look at how we sketch one. So initially the reaction is at equilibrium, everything's flatlined. So as far as you're concerned, the reaction is quote unquote over, it's done. But what happens if we disturb the equilibrium? What happens if we add a stress to this equilibrium? So in this case we are going to increase the concentration of A. By increasing the concentration of A, we've made it more likely for A to collide with B. This provides the forward reaction with the advantage. And as the reaction shifts forward, we will use up A to make AB. We'll use up B to make AB. And because we're making AB, the AB concentration will also increase. Now, let's double check our collision theory explanation with Le Chatelier's principle. According to Le Chatelier's principle, if we increase A, it's going to try to minimize that change by decreasing A, and that's what it's done. And so the net change in A is not as bad as it could have been. All right, so Le Chatelier is a good way to double check your work, but in the end, don't just blindly believe it. You must use collision theory to explain why and you're going in a certain direction, who gets the advantage. So let's sketch this all out in the graph below. We started off with an increase in A, so I want to see a sharp increase in the concentration of A. And this leads the reaction to move forward, so the concentration of A will decrease from that point on. But here's where we run into a little bit of a problem. So in this situation, you could draw the curve like this, so you notice that's decrease in the concentration of A. But you could also draw the curve like this, and you see a decrease in A as well. So both curves are showing a decrease in A over time. However, only one of these curves is correct, and that would be number 2. You see, the problem with curve number 1 is that the reaction doesn't cause a change in the concentration immediately. It's just flatlined, so it's like nothing's happening. Even though you dumped in a lot of A, you've increased the chances of A reacting with B, nothing's happening at the beginning. It only starts to happen, it only starts to change its concentration later in the game. But that doesn't make any sense. As soon as I dump a bunch of A molecules into my bucket, I've immediately given the forward direction an advantage. So immediately the A's should start colliding with B's, and the amount of A's present should decrease quickly because now you're starting to react them together to make ABs. But we're not seeing that. It's just flatline. It's like the concentration just is not changing. The A's remain the same. That doesn't make any sense. But with curve number 2, I see that immediate change in the concentration of A. As soon as I place a lot of A inside, it automatically starts reacting and starts decreasing. And that's what's happening. I see the immediate decrease in the concentration of A, and then it slowly flatlines out. All right, so do not draw curve number 1. I know that both of them show a decrease. They both show a decrease, but only one of the curves, and that's curve number 2, shows the proper decrease in the curve. If you draw the wrong curve, I will have to deduct marks. Another thing to keep in mind is that this is all about damage control, not damage reversal. We are going to create a new equilibrium, so I should not see the concentration of A return back to its old equilibrium state. So I shouldn't see it go back to its original concentration levels. I will have to deduct marks for that as well. So be careful, make sure you have the correct inflection in the curve, as well as maintaining the new equilibrium concentration, not the old equilibrium concentration. Now we're going to do the same thing with B. We're supposed to see a decrease in its concentration as it goes forward. It's being used up, and that's again what we see over here, a decrease in its concentration, again with the right curve. And finally, AB should also be increasing. But again, watch out for the curve. This is the correct one because we see an immediate change in its concentration. It's increasing immediately. I don't want to see a flat line where nothing happens as soon as I make that change. So just make sure you've got the correct inflection for this curve as well. Alright, so at this point I would like you to take a few minutes to complete the remaining curves, and then we will take it up together. Okay, here we go. Let's take a look at this one. Here we have a decrease in the B concentration. This in turn makes it less likely for the A and B to combine together because it's hard for them to find each other now. As such, the forward direction is disadvantaged and has a lower rate of reaction than the reverse direction, which has a greater rate of reaction. This allows our equilibrium to shift to the left, reducing the concentration of AB and increasing the concentration of B and A. Let's see if this all makes sense using Le Chatelier's principle. So we decrease the concentration of B, equilibrium shift to the left, and it's increasing the concentration of B again. And there's our damage control. It's not as bad as it could have been. So let's sketch all of this on the graph below. We'll first show the sharp decrease in the concentration of B, followed by an increase with the correct curve inflection, as well as the final equilibrium state being a new equilibrium and not the original equilibrium concentration. A will also see an increase in concentration, again with the correct curve, while AB will see a decrease in its concentration, again with the correct curve. Now be aware, sometimes these lines may cross each other, like this, but it's perfectly fine, so long as it's obvious which line belongs to which one. Just don't make it ambiguous like this. So whether it crisscrosses or remains separate, I'm not particularly concerned. I mean, you are just sketching the graph. You're not actually graphing it to scale, so it's not a huge deal. In our next scenario, we are increasing the pressure on our system. Unfortunately, the question is not explicit enough. It doesn't mention anything about a volume change. On a test, I'd be a little more explicit. I will mention that, yes, the increase in pressure will affect the volume. But in this case, we're just going to assume that a volume does change. So we are increasing the pressure. The volume is going to decrease because now it's being squeezed into a smaller volume. And that will result in a more crowded container, which is why you should see a sudden increase in concentration for each of the chemical compounds in this chemical reaction. Now, by making things more crowded, it's much easier for A and B to collide with one another. It's much easier for them to find each other. This results in the forward direction getting an advantage, reducing the concentrations of A and B as they combine together to move forward, and increasing the concentration of A2B. Now, let's double check with Le Chatelier's principle. We have increased the pressure of our system, so it needs to decrease the pressure of our system somehow. If you looked at the reactant side, on the left-hand side, we have 3 molecules, 2 A's and a B, but only 1 molecule on the right-hand side, on the product side. So by shifting the equilibrium forward, we're combining 3 molecules into 1. With fewer molecules, we have less of them colliding with the walls, and this in turn reduces the pressure on the system. So once again, we have increased the pressure, equilibrium shifted to the right, which resulted in a decrease in pressure. So Le Chatelier's principle checks out in this case. So let's sketch all of this in the diagram below. Both A and B will decrease with a proper curve and without reaching the original concentrations, while A2B will increase again with the proper inflection in the curve. In our next graph, we are again seeing a change in pressure, except this time it's a decrease in pressure. By decreasing the pressure, we are increasing the volume and making things less crowded for everyone. So we should see a sudden drop in all 3 concentrations. Now, according to Le Chatelier's principle, if I decrease the pressure, equilibrium should shift in a direction to increase the pressure. Looking at the top, on the left-hand side, the reactant side, we see there are 2 molecules. They are AA and BB, these 2 molecules. While on the right-hand side, the product side, we also have 2 molecules. One of them is an AB, and the second one is also an AB, which is denoted by this little coefficient here at the front to show that there are 2 of these AB molecules. So in which direction must I shift in order to increase the pressure? The answer is neither. Neither side provides an advantage. We've got 2 molecules bouncing against the walls in this case, but 2 molecules bouncing against the walls in this case. So neither shifting left nor shifting right will allow me to increase the pressure of my system. So this is another situation where you can't just blindly follow Le Chatelier's principle. You have to use collision theory to verify that it's going to be true. By decreasing the pressure, I've made it more difficult for these 2 to find each other because it's less crowded. So AA and BB have a much harder time colliding with one another. Well, same thing. By making it less concentrated, I have also made it more difficult for AB and AB to slam into each other, made it more difficult for them to find each other. So in both cases, we get a disadvantage. We went from an equilibrium where there was a high rate of reaction going in the forward and reverse direction to another equilibrium, but this one has a reduced forward rate of reaction and a reduced reverse rate of reaction. By reducing them both in the same way, I have not provided one direction with a greater advantage over the other. As such, we end up with a flat line in all 3 cases. Alright, so be careful. Don't just blindly use Le Chatelier's principle. In the end, take a look at collision theory to verify if what you're doing makes sense. In our next example, we see that the energy change for this reaction is a negative value, meaning that the reaction is losing energy. As such, I would write energy on the right-hand side on the product side because energy is being produced, being released by the system. Now, if we increase the temperature of the system, we provide the reverse direction with an advantage. As shown in this equation, going in the reverse direction requires additional energy input. There's no such requirement on the left-hand side, so going forward does not require additional energy input. Room temperature is more than enough energy to allow you to move forward. So any additional temperature increase you provide to the left-hand side doesn't really provide it with any additional benefit. It's kind of like a wasted benefit in that case. Whereas going in reverse does appreciate it and does require that additional energy input to move left. Thus, the reverse direction is advantaged in this case. In so doing, the concentration of A2B will decrease, while the concentrations of A and B will increase. Now, let's double check with Le Chatelier's principle. We are increasing the temperature, so providing more energy on this side and this side, but the energy increase on this side is kind of wasted, whereas this one is appreciated, which drives the reaction in reverse, causing A2B to decrease as well as the energy on this side, because we have to consume energy to split up the A2B and decompose it into these two compounds. So we are using up thermal energy and converting it into chemical potential energy, energy stored within the chemical bonds of these new compounds. And that, of course, results in a decrease in temperature, which is what we wanted to see. We increase the temperature, and now Le Chatelier's principle states that it's shifted to the left, and we've decreased that temperature, converting it into chemical potential energy, and allowing us to minimize that temperature change. So it could have been a lot higher, but instead it's not as bad as it could have been. All right, so let's convert all of this into our diagram below. Both B and A should increase, while A2B will decrease. In our final example, the change in energy for this reaction is a positive value. So that tells me I need to add energy into my system to drive the reaction forward. So in this case, it's an endothermic reaction. Since energy is required, I got to add into the system. It is going to be written on the reactant side. Again, we're going to change the temperature, but this time it's going to be a decrease in temperature. In so doing, we've made it very difficult to go forward because in order to go forward, I need energy. But here we are decreasing the energy, so it's hard for A and B to slam into each other with enough activation energy to go forward. Thus, the forward direction is disadvantaged, and the reverse reaction has a higher rate than the forward. As such, the equilibrium is going to shift to the left, decreasing the concentration of A2B as we move in this direction, while increasing the concentration of A and increasing the concentration of B. At the same time, chemical potential energy is being released as thermal energy, thus raising the temperature back up. So now the net temperature change is not as bad as it could have been, which is what we want. We have decreased the temperature in accordance with Chatelier's principle. By decreasing the temperature, we have shifted the equilibrium to the left, resulting in chemical potential energy being released as thermal energy. So we've increased the temperature, and yeah, Le Chatelier's principle checks out in this case. So let's take this information and sketch it on our graph below. We have A2B decreasing, while A and B are both increasing. Another thing that is expected of you is to be able to interpret these graphs of equilibrium changes. So let's take a look at the situation over here where everything's at equilibrium. I know this blue line over here looks like it's curved. It should be perfectly straight, all right? So we've had an equilibrium. At point A, I've introduced some sort of stress to the system. I've introduced a change to the system, and then I've allowed it to reach equilibrium again. At point B, I've done and introduced another stress, which again, I allow it to reach equilibrium. At point C, I've introduced another stress, and then allowed it to reach equilibrium. And then at point D, I've introduced one last stress. Even though it doesn't look like I've done anything, I definitely have done something here. So my question to you is, at each of these points, A, B, C, and D, what kind of stress could I have introduced into the system in order to allow it to force the graph to behave the way it has behaved in each of these scenarios? So let's give this a try. Take a moment, press pause, and then when you press play, we'll take it up together. All right. So at point A, you'll notice that there's a decrease, a sudden drop in the concentrations of all three substances. So something must have occurred to force all three substances to suddenly lose their concentrations. The most common thing that can do that to all three of them at the exact same time would be a pressure decrease. By decreasing the pressure, I've increased the volume. By increasing the volume, I made things less crowded. By making things less crowded, all three of them will have decreased their concentrations. Looking at this equation, we see that there are two molecules on the left-hand side, but only one molecule on the right. So if I have decreased the pressure, equilibrium will shift in a direction in order to increase that pressure. So which direction should it shift? Well, the answer is to the left. By shifting equilibrium in reverse, I go from one molecule to two molecules. So instead of just one molecule colliding with the walls of the container, we now have twice as many colliding with the walls of the container, which in turn increases the pressure. Let's see if that makes sense using collision theory. By decreasing their pressure and increasing the volume, we made it less likely for these two to find each other. If it's less likely for these two to find each other, the forward direction is disadvantaged, while the reverse direction has the advantage. So that does check out. So at point A, we have decreased the pressure. Now at point B, we see that both the green line, C2H4, and the blue line, H2, have increased, while the C2H6 has decreased. And the only way for this to happen is, again, if the equilibrium is shifting to the left. But you'll notice there's no sudden increase in either of these chemical compounds, so that tells me I didn't change any of these concentrations. So the only change left to me at this point is by changing the energy. But how can we drive the reaction in reverse? Well, by increasing the temperature. In so doing, I provide the reverse direction with the advantage, because as you can see on the left-hand side, no additional energy is required to move forward, but additional energy is required to go in reverse. So if I provide it with that additional energy, it's wasted advantage on this side, but it's a useful advantage on this side. And at that point, the C2H6 will decrease, while H2 and C2H4 will increase. So at point B, we have increased the temperature. Now at point C, I think it's pretty obvious. You can see that C2H6 has received a boost, again making the reverse direction more likely to occur. With more C2H6, more of them will break up per second. Again, that will result in a decrease in C2H6, which is what we see, while both H2 and C2H4 will increase. So at point C, we have increased the concentration of C2H6. All right, in the last situation, nothing's happening, and the only thing we can do to cause nothing to happen to equilibrium would be the addition of an inert gas or the addition of a catalyst, because neither of those two situations will result in an equilibrium shift. And that is our lesson on graphing equilibrium changes.